Hello everyone, I'm delighted to have the opportunity to present our work here. The title of our paper is Rethinking Knowledge Distillation with Raw Features for Semantic Segmentation. Knowledge distillation is a model compression and transfer learning technique where a small student model is trained to mimic a large teacher model, preserving acceptable performance with reduced model size. FitNets is a classical feature-based KD method that uses the feature map of the middle layer of the network as knowledge. Inspired by this, many feature-based KD approaches emerged later. Instead of distilling the raw features as in FitNets, they prefer to extract various forms of knowledge from raw features, such as the attention map, gramming matrix, pairwise similarity, and so on. However, this kind of knowledge is usually manually designed and rely on various previous knowledge as in traditional feature engineering. So in this paper, we aim to propose a simple and effective feature distillation method using raw features. The naive feature distillation minimizes the MSE loss between FS and FT. FS is the student feature, FT is the teacher feature. As shown in Figure 1, we found that the naive feature distillation is able to achieve good results and even surpasses some well-designed approaches for semantic segmentation. However, its performance is sensitive to the loss weight. For example, when the teacher is a PSPNet R101 and the student is PSPNet R18, it requires a large loss weight to get good results. Instead, a relatively small loss weight is appropriate when the teacher is UPNet SwimB and the student is UPNet SwimT. To figure out why the naive feature distillation is sensitive to the loss weight, we start by analyzing its loss function. From the perspective of vectors, we can reformulate Fs and Ft as the equation 2. N and M denote the magnitudes of Fs and Ft, and xy are unit vectors. Then the loss of a naive feature distillation can be reformulated as equation 3. The first term minimizes the magnitude difference, and the second term minimizes the angular difference, but is affected by the magnitude. We observe that the angular difference term is critical for the naive feature distillation, but the weight of the angular difference term is affected by the magnitude of the features. Since the magnitude of the features produced by different models may vary significantly, it is hard to determine a suitable loss weight for various models. Aiming to make the weight of the angular difference term independent of the feature's magnitude, we attempt to turn the magnitudes of the teacher and student features into constant values. A simple way is to perform L2 normalization, so we minimize the loss in equation 5. We can see that equation 5 essentially treats the entire features of a layer from the teacher or student as a vector, and minimizes the angular difference between them. The feature used for distillation in semantic segmentation is a fine-grained tensor that contains both spatial and channel dimensions. The features of different dimensions usually carry different information. Therefore, we argue that it is necessary to take the dimension of the feature into account, so we can also treat the features of a channel as a vector and minimize the angular difference between features of the same channel from the teacher and the student. And we can also treat the features of each spatial point as a vector, and minimize the angular difference between features of the same spatial point from the teacher and the student. The difference between LAD, CAD, and PAD is that the dimensions of the angular information used for distillation are different. Here is our distillation pipeline for semantic segmentation. We compute our angular distillation loss on backbone features and apply the conventional distillation loss on logits following previous approaches. We compare our method with recent KD approaches for semantic segmentation on Cityscapes, Pascal VOC, and ADE20K. Our method significantly improves the performance of baseline students without KD, and consistently outperforms other approaches by a large margin under various setups, especially on challenging ADE20K. Our method shows excellent robustness to the loss weight, which is the only hyperparameters in our method. We also compare our LAD, CAD, and PAD at different distillation positions. Our method works best at the backbone, then at the decoder, and worse at the prediction layer. LAD performs the best at the backbone. CAD exhibits the best robustness at different distillation positions. PAD performs the worst among our methods, but is still better than the naive feature distillation. The performance gap between LAD, CAD, and PAD indicates that the dimension of angular distillation is critical. We believe that the lack of spatial context is a reason for the poor results of PAD. As shown in Figure 6, PAD fails to make the student learn a spatially similar pattern of feature activations as the teacher. We also apply our method to object detection. Our method achieves competitive performance compared to state-of-the-art approaches. This indicates a promising generality of our method. At last, our main contributions are summarized as follows. First, we decompose the loss function of naive feature distillation into a magnitude difference term and an angular difference term, and point out the reason why it is sensitive to the loss weight. Second, we explore distilling angular information along different feature dimensions, and show that the dimension of angular distillation is critical for semantic segmentation. Third, without relying on the sophisticated knowledge of manual design, our method achieves the state-of-the-art distillation performance for semantic segmentation and is robust to hyperparameters. Thank you for your attention.